Okay, let me quickly make sure that I am connected and that we got things going. Alright. Yeah, oh man, it has been way too long. Apologies for the delay, just had some stuff going on, but now we are ready to get back into it, and I will I'll delay no longer. Chapter 16, Rings. Up to this point, we have studied sets with a single binary operation satisfying certain axioms, but we are often more interested in working with sets that have two binary operations. For example, one of the most natural algebraic structures to study is integers with the operation of addition and multiplication. These operations are related to each other by the distributive property. If we consider a set with two such related binary operations satisfying certain axioms, we have an algebraic structure called a ring. In a ring, we will add and multiply elements such as real numbers, complex numbers, matrices, and functions. 16.1. A non-empty set R is a ring if it has two closed binary operators, addition and multiplication. So we'll call this ring A, and we have this, our ring is A, and we have this one operation, plus from A times A to A, and dot A times A to A. Also, I should quickly note here, before further confusion arises, this times is what we're defining to be multiplication in the ring. This times is the Cartesian product. Alright, so we have the following properties. So first of all, we have plus is commutative or abelian. Actually, yeah, commutative is probably not the right word, is abelian. So we have a plus b is equal to b plus a. We have a plus b plus c. We have that plus is associative. Plus is associative. So a plus b plus c equals a plus b plus c. There's an element 0, so we have an identity element. So plus has identity. So there exists an element 0 such that a plus 0 equals 0 plus a equals a. And for every element there's a negative element. So actually, instead of putting that, we already wrote all this. But what this is actually saying is it's starting by saying that plus is an abelian. Oh gosh. Is an abelian group on A. Now, our other conditions is that A, B, or A times B times C is equal to A times B times C. And we also have that A, B plus C is equal to AB plus AC. That is correct. Oh yeah, we have that, and we also have its associated right multiplication equals BA plus BC. Alright, so what this is saying is that, notice that we're only defining, this is defining associative structure. We'll define a group structure for R later, but right now we only want something that naturally generalizes the distributive properties from multiplication. We have a group structure always confirmed on plus. We do not always have it confirmed on multiplication. Okay. This last condition, the distributive axiom, relates the binary operation of addition and multiplication. Notice that the first four axioms simply require that the ring be an abelian group under addition. So we could also have defined a ring to be an abelian group R plus together with a second binary operation satisfying the 5th and 6th conditions as given above. If there is an element 1 in R, such that 1 is not equal to 0. So let me also quick check something on the stream real quick. So, okay. So, 1 is not equal to 0 in a unidal ring. Ring implies A is, let me write this better. A is a ring. We say that R is a ring with unity or identity. So something important to note here is that if we can have 1 be equal to 0, we just define the entire ring to be 0. But we will basically never want to consider that case, considering it's very extremely trivial, considering it's literally 1 point. Alright, yeah. If there's an element 1, such that 1 is not equal to 0, and 1A equals A, 1 equals A for each element A in R, we say that R is a ring with unity or identity. So this basically gives, we'll see later on, there's a certain almost group structure on multiplication. You'll see what I mean by that. In this case, if it's a ring with unity, we have an identity element. A ring R for which AB is equal to BA, for all A, B, and R, is called a commutative ring. So AB equals BA is described as commutative. Oh god. I'll just write COMM to imply commutativity. A commutative ring R with identity is called an integral domain if for every A, this I won't do too much because it goes more into integral domains later, if for every A, B in R, such that AB is equal to 0, either A is equal to 0 or B is equal to 0. So let me carry this entire part to the whiteboard, and let me actually bring an example of something that is not an integral domain. So, okay, that's properly dragged over. So consider the integers mod 6. And it's very clear that using the equivalence classes, we have like all the actual axioms of a ring. So we can write plus, if we want to be specific, plus mod 6 times mod 6 is our ring structure. But consider 2 times 3 mod 6 is equal to 6 mod 6 is equal to 0 mod 6. We have 2 non-zero elements which multiply together to give us 0. Which means that z6, and we'll see as a slight preview, z sub n for n not prime will always give us not an integral domain. Alright. Let me bring back my previous notes real quick. Give me a second. Bring back my previous notes. Oh gosh, no, what am I doing? Okay. Oh, that's why. I have to be very careful with that. Make sure I have enough space. That'll be fine, yeah. Alright. A commutative ring R with identity is called an integral ring. A division ring is a ring R with an identity in which every non-zero element R is a unit. That is, each A and R with A not equal to 0, there exists an element A multiplicative inverse, such that the multiplicative inverse of A times A is equal to A times the multiplicative inverse of A is equal to 1. A commutative division ring is called a field. So basically what this is saying is a division ring is a ring, a division ring is a ring that is associative, has identity, and has inverses for every non-zero element. Which means that, as we'll see later, it actually means that a division ring is a ring such that the non-zero elements form a group under multiplication. We'll see that specifically later, that that 0 has absorption. Alright. And then, yeah, so from rings, we have commutative rings and integral domains. Integral domains are always defined to be commutative. Rings with identity must go to integral domains. And then division rings stem from rings with identity, and integral domains and division rings lead to fields. Alright, example 16.2. As we have mentioned previously, the integers form a ring. In fact, Is an integral domain. Certainly, if ab equals 0 for two integers a and b, either a equals 0 or b equals 0. However, z is not a field. There is no integer note mind here. It's going to be important to know what universe you're working in. That is the multiplicative inverse of 2, since 1/2 is not an integer. The only integers with multiplicative inverses are 1 and -1. Example 16.3. Under the ordinary operations of addition and multiplication, all the familiar number systems are rings. The rationals, the real numbers, and the complex numbers. Each of these rings is also a field. Example 16.4. All this is going to be similar to what I showed last time. We can define the product of two elements a and b in z sub n by ab mod n. For instance, z sub 12 5 times 7 equals 11 mod 12. Oh, I can make my voice a second. This product makes the abelian group z sub n into a ring. Certainly z sub n is a commutative ring. However, it may fail to be an integral domain. If we consider 3 times 4 is equivalent to 0 mod 12 in z mod 12. Notice here that this is a factorization for 12. It is easy to see that a product of two non-zero elements in a ring can be equal to 0. A non-zero element in a commutative ring is called a zero divisor if there is a non-zero element b such that ab is equal to 0. So basically, zero divisors are elements that can be multiplied to be taken to 0. In the previous example, 3 and 4 are zero divisors in z mod 12. Example 16.5. In calculus, the continuous real-valued functions on an interval ab form a commutative ring. For this, we just add or multiply point-wise the components of the function. So, like if f of x equals x squared and g of x equals cos x, then f plus g x is equal to fx plus g of x is equal to x squared plus cosine x, and f g of x is equal to fx g of x is equal to x squared cos of x. Example 16.6. The 2x2 matrices with entries in R form a ring under the usual operations of matrix addition and multiplication. This ring is non-commutative, since it is usually the case that AB is not equal to BA. Also, notice that we can have AB equals 0 when neither A nor B are 0. Example 16.7. For an example of a non-commutative division ring, we're going to have the representations of the quaternions through matrices. Okay. Let 1 be equal to 1, 0. I be equal to -1, 1. I'm not going to read these out in full order. You can read these. Where I squared is equal to -1. These elements satisfy the following relations. We have that I squared is equal to j squared is equal to k squared is equal to -1. Ij is equal to k. Jk is equal to L. Kl is equal to j. Ji is equal to -j. So notice we have non-commutativity here because of this property right here. Well, it's properly actually even called anti-commutativity there. Kj is equal to -i, and Ik is equal to -j. Let H consist of elements of the form A plus Bi plus Cj plus Dk, where A, B, C, and D are real numbers. Equivalently, H can be considered to be the set of all 2x2 matrices of the form alpha, beta, negative, beta, it's the conjugate of beta, which... Okay, I'm not actually going to keep too many notes on it now. The conjugate is just flipping the imaginary parts around. We can define addition and multiplication on H by either the usual matrix operations or in terms of the generators 1, I, j, and k. So, like, we just distribute it out when we just add it out, and we just get exactly what we need from here. Alpha, beta, gamma. Is that the multiplication looks complicated? It is actually a straightforward computation if we remember that we just add and multiply elements in H like polynomials and keep in mind the relationship between the generators I, j, and k. The ring H is called the ring of quaternions. Oh god, that scares me because I need way more exposure to quaternions. To show that the quaternions are a division ring, we must be able to find an inverse for each non-zero element. Notice that A plus Bi plus Cj plus Dk times A minus Bi minus Cj minus Dk equals A squared plus B squared plus C squared plus D squared. This element can be 0 if A, B, C, and D are all 0. So, if A plus Bi plus Cj plus Dk is not equal to 0, A plus bi plus cj plus dk times a minus bi minus cj minus dk over a squared plus b squared plus c squared plus d squared is equal to 1. Proposition 16.8. We're going back to the abstract ring theoretic stuff also. Let R be a ring with A, B elements in R. Then, A times 0 equals 0 times A equals 0. This is the absorption property of 0. A times minus B is equal to minus A times B is equal to minus AB. And negative A times negative B equals AB. So, to prove 1, observe that A0 equals A0 plus 0 equals A0 plus A0. Hence, A0 is equal to 0, because we can just subtract out by A0 on both sides. Similarly, 0A is equal to 0. For 2, we have AB plus A minus B is equal to A B minus B equals A0 equals 0. Consequently, negative AB equals A minus B, and similarly we have minus AB equals minus AB. Part 3 follows directly from 2, since negative A negative B equals negative A negative B equals negative negative AB equals AB. A lot of this is showing as well. It's a fairly simple proof, but it shows just how important the distributivity is in this. If we don't have distributivity, we don't even have this proof. Just as we have subalgebras, just as we have subgroups of groups, we have an analogous class of substructures for rings. Okay, I'm also going to put massive red warning signs at this. There are multiple times where subring means different things to different authors. If you're reading anything, especially like a commutative algebra text, always make sure you're aware of the author's intentions. Do your subrings have unity or not? Like, that is going to be a very important question in a majority of cases, and something that authors differ on depending on their applications of the theory. But anyways, enough stalling. A subring S of a ring R is a subset S of R, such that S is also a ring under the inherited operations from R. So notice here that we don't require that any elements specifically be in the subring. We simply require that it both be an abelian group under addition, so a abelian subgroup, and that if we multiply two elements in that subgroup, we get another element in the subgroup. Alright, example 16.9. The ring NZ is a subring of Z. Notice that even though the original ring may have identity, we do not require that its subring have an identity. We have the following chain of subrings. Z is a subset or subring, in this case Q, is a subring of R, is a subring of C under the canonical identifications. The following proposition gives us some easy criteria for determining whether or not a subset of a ring is indeed a subring. We will leave the proof as proposition as an exercise. I'm excited. Proposition 16.10. Let R be a ring and S a subset of R. Then S is a subring of R if and only if the following conditions are satisfied. First, S is not equal to the empty set. 2. RS is in S for all R and S in S. And 3. R minus S is in S for all R and S in S. As a little hint, I'll just say as well that we've already proven this, but just in different notation. Example 16.11. Let R equals M squared R be or M sub 2 of R be the ring of 2 by 2 matrices with entries in R. If T is the set of upper triangular matrices in R, i.e. the set of all matrices of the form AB0 to C for A, B, and C in R, then T is a subring of R. If A is equal to AB0C and B is equal to A give me a second, A prime, B prime 0, C prime, R in T, then clearly A minus B is also in T. Also, AB is equal to A prime, B prime, plus BC prime, 0, CC prime is in T. So this basically extends the example we worked on in previous exercises to a actual entire ring structure instead of just group structure. Integral domains and fields. Okay. Let us briefly recall some definitions. If R is a commutative ring, and R is a non-zero element in R, then R is said to be a zero divisor if there is some non-zero element S in R, such that R times S is equal to 0. A commutative ring with identity is said to be an integral domain if it has no zero divisors. If an element A in a ring with identity has a multiplicative inverse, we say that it is a unit. If every non-zero element in a ring R is a unit, we call it a division ring, and a commutative division ring is called a field. So let us first divide the Gaussian integers. Example 16.12. If I squared is equal to -1, then the set Z, we call this set Z adjoined I. What it is the set of all M plus Ni, for M and N and Z, forms a ring known as the Gaussian integers. It is easily seen that the Gaussian integers are a subring of the complex numbers, since they are closed under addition and multiplication. Let alpha be equal to A plus Bi be a unit in Z sub I. Then the conjugate of alpha is equal to A minus Bi is also a unit, since if alpha beta is equal to 1, then alpha conjugate beta conjugate is equal to 1. If beta is equal to C plus Di, then 1 is equal to alpha beta conjugate beta conjugate equals A squared plus B squared C squared plus D squared. Therefore, A squared plus B squared must be 1 or -1. Consequently, A plus Bi is equal to plus minus 1, or A plus Bi is equal to plus minus I. Therefore, units of this ring are plus minus 1 and plus minus I. Hence, the Gaussian integers are not a field. We will leave it as an exercise to prove that the Gaussian integers are an integral domain. Example 16.13. The set of matrices 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, and 0, 0, 0, with entries in Z sub 2, note the entries that we have over here, form a field. Example 16.14. The set Q adjoined square root of 2, that's how we pronounce it, is equal to A plus B square root of 2, A, B, and Q, is a field. The inverse of an element A plus B squared 2 and Q square root of 2 is A over A squared minus 2B squared plus minus B over A squared minus 2B squared square root of 2. We have the following alternate characterization of integral domains. Proposition 16.5, the cancellation law. Let D be a commutative ring with identity. Then D is an integral domain if and only if, for all non-zero elements A and D with AB equals AC, we have B equals C. So because of the previous group structure that we had, like the cancellation laws followed naturally. In the case of integral domains, we actually have to have a stipulation because we don't have a full group structure on multiplication. So proof. Let D be an integral domain. Then D has no zero divisors. Let AB be equal to AC with A not equal to 0. Then A, B minus C is equal to 0. Hence, B minus C is equal to 0, and B is equal to C. This step right here is where we use the integral domain. Conversely, let us suppose that the cancellation is possible in D. That is, suppose that AB equals AC implies B equals C. Let AB be equal to 0. If A is not equal to 0, then AB equals A0, or B is equal to 0. Therefore, A cannot be a zero divisor. The following surprising theorem is due to Wedderburn. Theorem 16.16. Every finite integral domain is a field. Alright, yeah, this is a very powerful thing. Let me get started before I read it. Proof. Let D be a finite integral domain, and D star be the set of non-zero elements of D. We must show that every element in D star has an inverse. For each A and D star, we can define a map lambda A from D star to D star by lambda A of D is equal to AD. This makes sense because if A is not equal to 0 and D is not equal to 0, then AD is not equal to 0. The map lambda A is 1 to 1, since for D1, D2, and D star, AD1 equals lambda AD1 equals lambda AD2 equals AD2. And this implies that D1 is equal to D2 by left cancellation. Since D star is a finite set, the map lambda A must also be on 2. Hence, for some D in D star, lambda AD is equal to AD is equal to 1. Therefore, A has a left inverse. Since D is commutative, D must also be a right inverse for A. Consequently, D is a field. So this also shows that, we'll show that the integers mod P for any prime, because they are all integral domains, automatically makes them finite fields, which is a really strong statement. From here. For any non-negative integer n and any element r in a ring, we write r plus on and on, n times r as nr. So we have, I'll just sneak a horrible note up here, n Note that this is an action of Z on R. And times. Alright, we define the characteristic of a ring R to be the least positive integer n, such that n acting on R equals 0 for all R in R. If no such integer exists, then the characteristic of R is defined to be 0. We will denote the characteristic of R by car of R. So, example 16.7. For every prime p, Z sub p is a field of characteristic p. By proposition 3.4, every non-zero element in Z sub p has an inverse. Hence, Z sub p is a field. If A is any non-zero element in the field, then PA is equal to 0, since the order of any non-zero element in the abelian group Z sub p is P. Lemma 16.18. Let R be a ring with identity. If 1 has order n, then the characteristic of R is n. So proof. If 1 is order n, then n is the least positive integer such that n1 is equal to 0, such for all R in R, nr is equal to n1r is equal to n1r is equal to 0r is equal to 0. On the other hand, if there is no positive, if no positive n exists such that n1 is equal to 0, then the characteristic of the ring is 0. So the characteristic of the ring is determined by the characteristic of the identity. Now, theorem 16.19. The characteristic of an integral domain is either prime or 0. Ooh, this is spicy. So let D be an integral domain, and suppose that the characteristic of D is n, with n not equal to 0. If n is not prime, then n is equal to ab, where 1 is less than a is less than n, and 1 is less than b is less than n. By lemma 16.18, we need only consider the case n1 equals 0. Since 0 is equal to n1 is equal to ab1 is equal to a1b1, and there are no zero divisors in D, either a1 is equal to 0 or b1 is equal to 0. Hence, the characteristic of D must be less than n, which is a contradiction. Therefore, n must be prime, so we can't make this factorization. 16.3. Ring homomorphisms and ideals. Alright, so this is where I will clear up my board once more, because we will probably need some space. Okay. In the study of groups, a homomorphism is a map that preserves the operation of a group. Similarly, a homomorphism between rings preserves the operation of addition and multiplication in the ring. More specifically, if R and S are rings, then a ring homomorphism. So I'm going to be using a bunch of abuses of notation here. R plus S. Notice that this is the addition in S, and this is the addition in R. We make this subtle identification so that we don't have to write with different notation all the time. We just assume that by the context of where the domain takes it, that's how we understand the addition. And phi of R S is equal to phi of R phi of S. Alright. If phi from R to S is a one-to-one and onto ring homomorphism, then phi is an isomorphism of rings. The set of elements that a ring homomorphism maps to 0 play a fundamental role in the theory of rings. For any ring homomorphisms phi from R to S, we define the kernel of a ring to be the set kernel of phi is the set of R in R, such that phi R is equal to 0. So it's the same kernel as previous, and we can just note that, like, this still follows from the definition of the... Oh, give me a second to properly think about how to explain this. Let me think here. Yeah, it still follows that it's a subgroup, an abelian subgroup, because we have the same kernel. The kernel is defined in the exact same way. First of all, this is not only a map between rings, this is a map between abelian groups, because it has the underlying abelian group structure that we're respecting. So we are literally just pulling the definition straight from that. Example 16.20. For any integer n, we can define a ring homomorphism from phi to z mod n by a goes to a mod n. This is indeed a ring homomorphism, since phi of a plus b is equal to a plus b mod n is equal to a mod n plus b mod n is equal to phi of a plus phi of b. These are a mod n. Note here, this is definitely something. So this is a mod n plus b mod n. This should all be mod n here. And phi of ab is equal to ab mod n is equal to a mod n times b mod n equals phi of a, phi of b. The kernel of the homomorphism is nz, which, as you might have noticed earlier, is also a subring. Alright, example 16.21. Let's see AB be the set of ring of continuous real-valued functions on an interval AB as an example 16.5. Oh shoot, also, okay, I just realized that some of you guys watching may not have experience with continuous functions, like, rigorously. So, if you haven't taken, like, real analysis or anything that requires that, just think of your standard definition of continuous. There is a very nice version of it, and a very nice topological version of it. But if you don't know the definition, that's fine. Just consider it to be nice functions. So let's see if AB be the ring of continuous real-valued functions on an interval AB as an example 16.5. For a fixed alpha in AB, we can define a ring homomorphism phi alpha from CAB to R by phi of A, f, is equal to f of alpha. So we basically evaluate our function to get a real number. This is a ring homomorphism, phi a f plus g equals f plus g alpha equals f alpha plus g alpha, and then we have these respective as well multiplication rule. And the ring homomorphisms of the type phi alpha are called evaluation homomorphisms, which this seems really subtle, but I'm just going to say there's so much more behind the hood with this. In the next proposition, we will examine some fundamental properties of ring homomorphisms. The proof of the proposition is left as an exercise. So proposition 16.22. Let phi from R to S be a ring homomorphism. If R is a commutative ring, then the image of R, phi of R, is a commutative ring. Phi of 0 is equal to 0. If 1R and 1S are the identities for R and S, and phi is onto, then we map the identities to the identities. And if R is a field, and phi R is not equal to the empty set, or not equal to the 1-point set, then phi R is a field. In group theory, we found that normal subgroups play a special role. These subgroups have nice characteristics that make them more interesting to study than arbitrary subgroups. In ring theory, the objects corresponding to normal subgroups are a special class of subrings called ideals. Alright, an ideal in a ring R is a subring I of R, such that if alpha is an I and R is an R, then both AR and RA are an I. So, okay. This is weird. So, I as a subset of R is an ideal if first it does define explicitly if I is a subring R I IR subset of I for all R in R. So what this means is that if we multiply any element in I by any element in the ring, we get another element in I. Which it might seem weird. Here's an example. Think of like 2 times the integers in the integers. Well, if we take an integer like 2a and we multiply it by any integer b, it's going to be equal to 2 times 2a times b. Which means that if we multiply any element in 2z by any real number at all, we're going to be able to take out that 2 because of the multiplication property. And we're going to be able to like go back to saying that like, give me a second. We're going to be able to go back and say that like, hey, we have this structure on here that takes elements in z to elements in 2z. If that makes sense. But basically, the idea that this comes about from is like the fact that we can like take out this 2 and then it just like distributes off there. This will also be an example of a principal ideal, but I'm not going to worry about that right now. So I'll keep that up there on the board. Oh man. Alright. An ideal is alright, then both alright. Yeah. Okay. Example 16.23. Every ring R has at least two ideals, 0 and the whole ring. These ideals are called the trivial ideals. Let R be a ring with identity, and suppose that I is an ideal in R, such that 1 is in I. Since for any R in R, R1 is equal to R in I by the definition of an ideal, I is equal to R. So if an ideal contains 1, it contains the whole ring. Example 16.24. If A is any element in the commutative ring R with identity, then the set A, Langle A Wrangle, equals AR, or AR with R and R, is an ideal in R. So basically, also note here the important condition commutative ring. We could generalize this if we wanted to arbitrary rings by defining to be equal to the set of all like RAS with R, S, and R. But the important thing to note here is that, especially in like, this is the ideal generated by 2, because any element can be written in the form 2a, which is just saying that we take the set of all integers such that it's 2 times that integer. Give me a second. Okay, yeah. Certainly, Langle A Wrangle is non-empty, since both 0 is equal to A0 and A is equal to A1 are in A. The sum of two elements in A is again in A, since AR plus AR prime is equal to AR plus R prime. Once again, where that distributivity comes in so necessary. The inverse of AR is negative AR is equal to A negative R is in A. Finally, if we multiply an element AR in A by an arbitrary element S in R, we have SAR equals ASR by commutativity. Therefore, the ideal generated by A satisfies the definition of an ideal. So if R is a commutative ring with identity, then an ideal of the form Langle A Wrangle is called a principal ideal. And there'll also be, later on, it should be important to note that there are some domains where not every ideal is principal, and there are some domains where every ideal is principal. So this idea will come back later in more detail. Theorem 16.25. Every ideal in the ring of integer z is a principal ideal. Oh, how perfect. Proof. The zero ideal 0 is a principal ideal since 0 is equal to 0, or the principal ideal generated by 0 is equal to 0. If I is any non-zero ideal in z, then I must contain some positive integer m. There exists a least positive integer n in I by the principle of well-ordering. Now, let A be any element in I using the division algorithm. We know that there exist integers q and r such that A equals mq plus r, where 0 is less than or equal to r is strictly less than n. The equation tells us that r is equal to a minus nq in I, but r must be 0 since n is the least positive element in I. Therefore, a is equal to nq, and I is equal to the principal ideal generated by n. Okay. Set nz is an ideal in the ring of integers. If na is in nz and b is in z, then nab is in nz as required. In fact, by theorem 16.25, these are the only ideals of z. Proposition 16.27. The kernel of any ring homomorphism, phi from R to S, is an ideal in R. Proof. We know from group theory that kernel of phi is an additive group of R. Suppose that R is in R and A is in kernel of phi. Then we must show that AR and RA are in kernel of phi. However, phi AR is equal to phi of A, phi of R is equal to 0, phi of R is equal to 0, and phi of RA is equal to phi of R, phi of A is equal to phi of R 0 is equal to 0. So this shows that their multiplication is in the kernel. So remark 16.28. In our definition of the ideals, we require that Ri is a subset of I, and IR is a subset of R for all R and R. Some ideals, such ideals are referred to as two-sided ideals. We can also consider one-sided ideals. That is, we may require only that either Ri is a subset of I, or IR is a subset of I for R and R, holds, but not both. Such ideals are called left and right ideals, respectively. Of course, in a commutative ring, any two ideals must be two-sided. In this text, we will concentrate on two-sided ideals. Yeah, because in in commutative algebra, you don't even have to worry about this distinction at all. In non-commutative algebra, you do have to worry about the distinction a bit more. So theorem 16.29. Let I be an ideal of R. The factor group R over I is a ring with multiplication defined by R plus I times RS plus I is equal to RS plus I. Note that we're able to define the factor group in terms of the abelian groups. And because every subgroup of an abelian group is normal, we can define this always. It's just kind of like how we can define the ring structure on this. That is the main difficulty. So R plus I times S plus I is equal to RS plus I. Proof. We know that R over I is an abelian group under addition. Let R plus I and S plus I be an R over I. We must show that the product R plus I times S plus I is equal to RS plus I is independent of the choice of coset. That is, if R prime is an R plus I and S prime is an S plus I, then R prime S prime must be an RS plus I. Since R prime is an R plus I, there exists an element A and I such that R prime equals R plus A. Similarly, there exists a B and I such that S prime is equal to S plus B. Notice that R prime S prime is equal to R plus A, S plus B is equal to RS plus AB AS plus RB plus AB. And AS plus RB plus AB is an I, since I is an ideal. And we're multiplying the entire thing. Yeah, okay. Consequently, R prime S prime is an RS plus I. We will leave as an exercise the verification of the associative law from multiplication and the distributive laws. The ring R over I, or R mod I, in theorem 16.29, is called the factor or quotient ring. Just as with group homomorphisms and normal groups, there is a relationship between ring homomorphisms and ideals. Theorem 16.30. Let I be an ideal of R. The map phi from R to R over I, defined by phi of R is equal to R plus I, is a ring homomorphism of R onto R over I with kernel I. Proof. Certainly, phi from R to R over I is a surjective abelian group homomorphism. It remains to show that phi works correctly under ring multiplication. Let R and S be an R. Then phi R times phi S is equal to R plus I, S plus I is equal to RS plus I is equal to phi of RS, which completes the proof of the theorem. The map phi from R to R over I is often called the canonical or natural ring homomorphism. In ring theory, we have homomorphism theorems relating ideals and ring homomorphisms similar to chapter 11. We will prove only the first isomorphism theorems. Oh wait, I skipped a line. In ring theory, we have isomorphism theorems relating ideals and ring homomorphisms similar to the isomorphism theorems for groups that relate normal subgroups and homomorphisms in chapter 11. We will prove only the first isomorphism ring theorem for rings in this chapter, and leave the other proofs of the other two theorems as exercises. As of the proofs, all of the proofs are similar to the proofs in the first isomorphism theorem for rings. So our first isomorphism theorem is that if R onto phi, if R onto S, phi is we might as well assume it's a surjective homomorphism, because we show that the image is a, how do I want to say this? The image is a ring, subring of S, so we can always just define a ring homomorphism going to the image. So we can assume it's a surjective homomorphism. So if we have that, and we define, I'll use some category theoretic commonalities, and we just define this with the understanding that if it has no labels, it's the canonical map. There is a unique ring isomorphism eta. Ring isomorphism eta that completes this triangle, such that if we factor through R over I, and then we apply eta, so we could call this natural map psi, and this has the property that phi is equal to eta composed with psi. Alright, then there's isomorphism over the quotient groups. Yeah. I just mixed up my size and phi's with the notation they commonly use. So proof. Let K is equal to kernel of psi. By the first isomorphism theorem, oh gosh, you know what, I'm gonna just give me a second. I'm gonna quick relabel things on here, otherwise it's gonna just like frustrate me to no end. Okay. This is a psi. This is a phi. This is a kernel of psi. Yeah, okay. And we want that psi is equal to eta. Oh, that's definitely an eta phi. A K kernel of psi. By the first isomorphism theorem for groups, there exists a well-defined group homomorphism, eta from R over K to psi of R, defined by eta of R plus K is equal to psi of R for the additive abelian groups R and R over K. To show that this is a ring homomorphism, we need only show that the multiplication structure is respected. But eta R plus K, S plus K, is equal to eta RS plus K, is equal to psi of RS, is equal to psi of R psi of S, is equal to eta R plus K, eta S plus K. And the second and third isomorphisms theorems are just like the same thing, except we replace the word like ring, the word group with ring, subgroup with subring, and normal subgroup with ideal. Yeah, literally just that. The correspondence theorem. Let I be an ideal of a ring R. Then S goes to S over I is a one-to-one correspondence between the set of subrings S containing I and the set of subrings of R over I. Furthermore, the ideals of R containing I correspond to ideals of R over I. So, maximal and prime ideals. In this particular section, we are especially interested in certain ideals of commutative rings. These ideals give us special types of factor rings. More specifically, we would like to characterize those ideals I of a commutative ring such that R over I is an integral domain or a field. So, a proper ideal M of a ring R is a maximal ideal of R if the ideal M is not a proper subset of any ideal of R except R itself. So basically, a maximal ideal M is defined by this. So, if M is a proper subset of K, is a ideals. I'll quick right here. If we have this, then K is equal to R. That is what implies M is maximal. Okay. Yeah, theorem 16.35. Let R be a commutative ring with identity and M an ideal in R. Then M is a maximal ideal of R if and only if R over M is a field. Proof. Let M be a maximal ideal in R. If R is a commutative ring, then R over M must also be a commutative ring. Clearly, 1 plus M acts as an identity for R over M. We must also show that every non-zero element in R over M has an inverse. If A plus M is a non-zero element in R over M, then A is not M in M. Define I to be the set RA plus M for R in R and M in M. We will show that I is an ideal in R. The set I is non-empty since 0A plus 0 is equal to 0 is an I. If R1A plus M1 and R2A plus M2 are two elements in I, then R1A plus M1 minus R2A plus M2 equals R1 minus R2A plus M1 minus M2 is an I. Also, for any R in R, it is true that Ri is a subset of I. Hence, I is closed under multiplication and satisfies the necessary conditions to be an ideal. Therefore, by proposition 16.10 and the definition of ideal, I is an ideal properly containing M. Since M is a maximal ideal, I is equal to R. Consequently, by the definition of I, there must be an M in M and an element B in R, such that 1 is equal to AB plus M. Therefore, 1 plus M is equal to AB plus M is equal to BA plus M is equal to a plus m, b plus m. Conversely, suppose that M is an ideal and R over M is a field. Since R over M is a field, it must contain at least two elements. 0 plus M is equal to M, and 1 plus M. Hence, M is a proper ideal of R. Let I be any ideal properly containing M. We need to show that I is equal to R. Choose an element in I, but not in M. Since A plus M is a non-zero element in a field, there exists an element B plus M and R over M, such that A plus M times B plus M is equal to AB plus M is equal to 1 plus M. Consequently, there exists an element M and M, such that AB plus M is equal to 1, and 1 is an I. Therefore, R1 is equal to R and I for R and R, and consequently I is equal to R. Whew, that's a lot, okay. That was a lot, gosh dang, okay. But it all makes sense, Example 16.36. Let PZ be an ideal in Z, where P is prime. Then PZ is a maximal ideal, since Z over PZ, which is isomorphic to ZP, is a field. A proper ideal P in a commutative ring R is called a prime ideal if whenever AB is in P, then either A is in P or B is in P. Let's check this. Is it possible? Yeah, you can define them non-commutatively, but they're a pain. So we're just going to worry about the commutative case. So AB is in P implies A is in P or B is in P. So example 16.37. It is easy to check that the set P equals Z to 0, 2, 4, 6, 8, 10 is an ideal in Z12. This ideal is prime. In fact, it is a maximal ideal. Proposition 16.38. Let R be a commutative ring with identity 1, where 1 is not equal to 0. Then P is a prime ideal in R, if and only if R over P is an integral domain. So first, let us assume that P is an ideal in R, and R over P is an integral domain. Suppose that AB is in P. If A plus P and B plus P are two elements of R over P, such that A plus B times B plus P is equal to 0 plus P is equal to P, then either A plus P is equal to P or B plus P is equal to P. This means that either A is in P or B is in P, which shows that P must be prime. Conversely, suppose that P is prime, and A plus P, B plus P is equal to AB plus P is equal to Z plus P is equal to P. Then AB is in P. If A is not in P, then B must be in P by the definition of a prime ideal. Hence, B plus P is equal to 0 plus P, and R over P is an integral domain. Example 16.39. Every ideal in Z is of the form NZ. The factor ring Z over NZ, which is isomorphic to Z mod N, is an integral domain only when N is prime. It is actually a field in this case, as we showed earlier with I forget his name. It was the guy's name who began with a W. I'm not going to mispronounce it here. It is actually a field. Hence, the non-zero prime ideals in Z are the ideals PZ, where P is prime. This example really justifies the use of the word prime in our definition of prime ideals. Since every field is an integral domain, we have the following corollary. Corollary 16.40. Every maximal ideal in a commutative ring with identity is also a prime ideal. So, okay, let me grab a drink of coffee. Alright. Emil Noether, one of the outstanding mathematicians of the 20th century, was born in Erlangen, Germany in 1882. She was the daughter of Max Noether, a distinguished mathematician at the University of Erlangen, together with, she was the daughter of Max Noether, a distinguished mathematician at the University of Erlangen. Together with Paul Gordon, Emmy Noether's father strongly influenced her early education. She entered the University of Erlangen at the age of 18. Although women had been admitted to universities in England, France, and Italy for decades, there was great resistance to their presence at universities in Germany. Noether was one of the only two women among the university's 986 students. After completing her doctorate under Gordon in 1907, she continued to do research at Erlangen, occasionally lecturing when her father was ill. Noether went to Göttingen, I'm going to mispronounce that, to study in 1916. David Hilbert and Felix Klein tried unsuccessfully to secure her an appointment at Göttingen. Some of the Give me a second. I can't read. Some of the faculty objected to women lecturers, saying, "What will soldiers think when they return to our universities and are expected to learn at the feet of a woman?" Hilbert, annoyed at the question, reasonably, responded, "Mein Herren, I do not see that the sex of a candidate is an argument against her admission as a Privatdozent. After all, the Senate is not a bathhouse." At the end of World War I, attitudes changed and conditions greatly improved for women. After Noether passed her habilitation examinations in 1919, she was given a title and was paid a small sum for her lectures. In 1922, Noether became a Privatdozent at Göttingen. Over the next 11 years, she used axiomatic methods to develop an abstract theory of rings and ideals. Though she was not good at lecturing, Noether was an inspiring teacher. One of her many students was B.L. van der Waerden, author of the first text treating abstract algebra from a modern point of view. Some of the other mathematicians Noether influenced or closely worked with were Alexandrov, I actually didn't know that, Artin, Brouwer, Korat, Hasse, Hopf, Pontryagin, oh god, I hope I pronounced that right, von Neumann, and Weil. One of the high points of her career was an invitation to address the International Congress of Mathematicians in Zurich in 1932. In spite of all the recognition she received from her colleagues, Noether's abilities were never recognized as they should have been during her lifetime. She was never promoted to full professor by the Prussian Academy bureaucracy. In 1933, Noether, who was Jewish, was banned from participation in all academic activities in Germany. She emigrated to the United States, took a position at Bryn Mawr College, and became a member of the Institute for Advanced Study at Princeton. Noether died suddenly on April 14, 1935. After her death, she was eulogized by such notable scientists as Albert Einstein. Yeah, just a thing to say, Noether's contributions to abstract algebra are kind of ridiculous. Like, abstract algebra would not be where it is today without Emmy Noether. So this, extremely long historical note is very much justified. Anyways. 16.5. An application to software design. The Chinese remainder theorem is a result from elementary number theory about the solutions of simultaneous congruences. The Chinese mathematician Sun Si, I hope I pronounced that right, wrote about the theorem in the 1st century AD. This theorem has some interesting consequences in the design of software for parallel processors. Lemma 16.41. Let m and n be positive integers such that the greatest common divisor of m and n is equal to 1. Then for a, b, and z, the system x is congruent to a mod n, and x is congruent to b mod n, has a solution. If x1 and x2 are two solutions of the system, then x1 is congruent to x2 mod mn. Proof. The equation x is congruent to a mod n has a solution, since a plus km satisfies the solution for all k and z. We must show that there exists an integer k1 such that a plus k1m is congruent to b mod n, and is equivalent. Oh, give me a second. Huh. That's some very bad snow outside. Hopefully I don't have internet issues. Since m and n are relatively prime, there exist integers s and t such that ms plus nt is equal to 1. Consequently, b minus a ms is equal to b minus a nt. Or, b minus a s times m is congruent to b minus a mod n. Now, let k1 be equal to b minus a times s. To show that any two solutions are congruent module mn, let C1 and C2 be two solutions of the system. That is, Ci is congruent to A, and Cij is congruent to B, mod m and mod n respectively, for I is equal to 1, 2. Then C2 is congruent to C1 mod m, and C2 is congruent to C1 mod n. Therefore, both m and n divide C1 minus C2. Consequently, C2 is congruent to C1 mod mn. Example 16.42. Let us solve the system x is congruent to 3 mod 4 and x is congruent to 4 mod 5. Using the Euclidean algorithm, we can find integers s and t such that 4s plus 5t is equal to 1. Two such integers are s equals 4 and t equals negative 3. Consequently, x is equal to a plus k1m is equal to 3 plus 4k1 is equal to 3 plus 4, 5 minus 4, 4 is equal to 19. From here, we have the Chinese remainder theorem. Let n1, n2, all the way to n sub k be positive integers such that the greatest common divisor of ni and nj is 1 for I not equal to j. So for any two, you pick any two of these that are different and they'll have a greatest common divisor of 1. Then for any integers, alpha 1 all the way to alpha k, any integers, the system x is congruent to a1 mod n1, x is congruent to a2 mod n2, all the way to x is congruent to ak mod nk, has a solution. Furthermore, the solutions of the system are congruent modulo n1, n2, all the way to nk. Proof. We will use mathematical induction on the number of equations in the system. If there are k equals 2 equations, then the theorem is true by lemma 16.41. Now, suppose that the result is true for a system of k equations or less, and say that we wish to find a solution of the system, but we append one extra condition to it. Considering the first k equations, there exists a solution that is unique modulo n1 to nk, say a. Since n1 all times nk, and nk plus 1 are relatively prime, the system x is congruent to a mod n1 times on and on times nk, and x is congruent to ak plus 1 mod nk plus 1, has a solution that is unique modulo n1 all the way to nk plus 1 by the lemma. So we basically use the previous solution to reparameterize it in terms of two separate equations. Example 16.44. Let us solve the system x is congruent to 3 mod 4, x is congruent to 4 mod 5, x is congruent to 1 mod 9, and x is congruent to 5 mod 7. From example 16.42, we know that 19 is the solution of the first two congruences, and any other solution of the system is congruent to 19 mod 20. Hence, we can reduce the system to a system of 3 congruences. X is congruent to 19 mod 20, x is congruent to 1 mod 9, and x is congruent to 5 mod 7. Solving the next two equations, we can reduce the system to x is congruent to 19 mod 180, and x is congruent to 5. Solving this last system, we find that 19 is the solution for the system that is unique up to modulo 1260. One interesting application of the Chinese remainder theorem is in the design of computer software. One interesting application of the Chinese remainder theorem in the design of computer software is that the theorem allows us to break up a calculation involving huge integers into several less formidable cases. A computer will handle integer calculations only up to a certain size due to the size of its processor chip, which is usually a 32 or 64-bit processor chip. For example, the largest integer available on a computer with a 64-bit processor chip is 2 to the 63 minus 1. I'm not even going to try to read that whole thing out loud. Larger processors such as 128 or 256-bit have been proposed or are under development. There is even talk of a 512-bit processor chip. The largest integer such that a chip could store will be the largest integer such that the largest integer that such a chip could store will be 2 to the 511 minus 1. This number is ridiculous. It's a 154-digit number. However, you only have to deal with much larger numbers to break sophisticated encryption schemes. Special software is required for calculations involving larger integers which cannot be added directly by the machine. By using the Chinese remainder theorem, we can break down large integer additions and multiplications into calculations that the computer can handle directly. This is especially useful in parallel processing computers, which have the ability to run several programs concurrently. Most computers have a central processing unit, called the CPU, containing one processor chip and can add only 2 members at a time. To add a list of 10 numbers, the CPU must do 9 additions in sequence. However, a parallel processing computer has more than one CPU. A computer with 10 CPUs, for example, can perform 10 different additions at the same time. If you want to take a large integer and break it down into parts, sending each part to a different CPU, then by performing several additions or multiplications simultaneously on those parts, we can work with an integer that the computer would not be able to handle as a whole. So example 16.45. Suppose that we wish to multiply 2134 by 1531. We will use the integers 95, 97, 98, and 99 because they are relatively prime. We can break down each integer into 4 parts. So 2134 is congruent to 44 mod 95, 2134 is congruent to 0 mod 97, 2134 is congruent to 76 mod 98, and 2134 is congruent to 55 mod 99. So we have these different systems. Multiplying the corresponding equations, we get these monstrosities. Each of these 4 computations can be sent to a different processor if our computer has several CPUs. By the above calculation, we know that 2134 times 1531 is a solution of the system x is congruent to 9 mod 95, x is congruent to 0 mod 97, x is congruent to 30 mod 98, and x is congruent to 55 mod 99. The Chinese remainder theorem tells us there are solutions unique up to modulo 95 times 97 times 98 times 99 equal to 89,403,930. Solving the system of congruences for x tells us that 2134 times 1531 is equal to 3267154. The conversion of the computation into the 4 subcomputations will take some computing time. In addition, solving the system of congruences will also take considerable time. However, if we have many computations to be performed on a particular set of numbers, it makes sense to transform the problem as we have done above and to perform the necessary calculations simultaneously. So not Sage, please no. So what is the fundamental theorem, oh my gosh. What is the fundamental difference between groups and rings? Rings are a priori supposed to be abelian, and they have a multiplication structure. A structure that acts nicely on the abelian structure, left and right. Give 2 characteristics of an integral domain. Give me a second. Give 2 characteristics of an integral domain. One is that a plus or a times b equals 0, implies that either a or b equals 0, but it also implies that how do I have an integral domain? Okay, let me think about how they specifically want this. Oh gosh, my brain is blanking. Why is it blanking? Because I know there's stuff about... Oh wait, yeah, what am I thinking? I'm being dumb. I'm being very dumb. So, AB equals 0 implies A equals 0 or B equals 0. Or equivalently, AB is equal to AC implies that B is equal to C. These are the same as saying that we have an integral domain. Alright, provide 2 examples of a field, one infinite, one finite. The integers mod p and the integers. He was Arthur, one of the most important abstract algebrists of all times, who also worked in a lot of fields of like topology and did a bunch of algebra related stuff there, and not even to mention Noether's theorem in physics, which if you're in physics you know. Speculate on a computer program. Nah, I'm good. Alright, so we just have exercises. But we have a fair number of exercises. So, I guess intermission time? Alright, it was a bit of a delay, but I'm back. And I'm ready to get going again. So let's just start on these exercises. Alright, everything's set up correctly. Wait, let me make sure my mic is actually on. Yes, it is actually on. Let's go. So which of the following sets are rings with respect to the usual operations of addition and multiplication? If the set is a ring, is it also a field? So, oh gosh. So 7z. One way to do this is to note we have the ring homomorphism from z to z mod 7, the canonical homomorphism, and 7z is equal to the kernel of phi, which makes it not only a ring, a subring, or proper, but it also makes it an ideal. So for 7z, yes. Alright, z mod 18. Oh yeah, 7z, is it a field? No, because like the integers aren't even a field. So z mod 18, for this, we'll note that z mod 18 is equal to z mod 9 times 2. We'll take for granted that z mod n is a ring for any n. We'll take that for granted. But because z mod 18 is equal to z mod 9 times 2, 9 times 2 is equal to 0 mod 18. So z mod 18 is not, so z mod 18 is not a field. I should also show, I don't know if they showed already, that that having that multiplicative inverse implies that you have a field. But like, suppose that a times b is equal to 0 for a, b not equal to 0 in a field. Then b negative 1, a negative 1, ab is equal to 0, which gets us that 1 is equal to 0, which is false because we assume our ring has unity and so has an element 1 that is different from 0. So basically every field, because of this, is an integral domain. So if we can simply show that something is not an integral domain, it automatically shows that it's not going to be a field in the first place. Alright. Q adjoins square root of 2. Yeah, let's work through this. So a plus b root 2, c plus d root 2, so we have that. Let me think about how to properly write this. So we have, yeah, we define multiplication through the distributive property AC plus 2BD plus AD plus BC square root of 2. We define it like this. And it should be obvious from here that we do have our normal, just because of our normal stuff that we have on the integers, that we have on the rationals even, that it follows that this does define a well-defined ring structure. And previously, even in the book, they computed the inverse. So this will be a field. I'm not going to go into more details than that because those computations get ugly. This is a field, yes, because we included the d squared root of 6. Otherwise, if we didn't do that, it would be a mess, and it wouldn't be. And just generally, I'll just say in advance that this is an example of adjoining an element to a field to get an extension field. I will just leave it at that. There's more stuff to it. So z mod squared, z adjoins square root of 3. This should be a ring, yeah. Yeah, this will be a ring under our commonly identified things, but it will not be a field, considering, like, even z is not a field. So, like, there's still no, like, 1 over 2 in this. So r is equal to a plus, yeah, okay. So for this is a more interesting example right here, example F. So suppose we have a plus, let's literally just have, let's not worry about it, cube root of 3 times cube root of 3. This is equal to the cube root of 3 squared, which is equal to the cube root of 9. So basically what we want to show is that suppose there's some a such that a times cube root of 3 is equal to the cube root of 9. Then this gives us that a cubed times 3 is equal to a cubed times 3 is equal to 9, which implies that a cubed is equal to 3, which implies that a is equal to the cube root of 3. Which this, if I remember correctly, I'm just going to go on a limb here, this is not rational. Yeah, this will not be rational. And as such, what a must be, it cannot be, which means that, like, the cube root of 9 is not actually included in our field, or is not included in our ring. So we actually don't even have enough structure to get a ring structure on this. If we adjoined cube root of 9, then if I remember correctly, it's fine, but with how it's currently defined, it's just not. So z sub I, a plus bi. Yeah, as you see here, when we adjoin cube root of 3 to the integers, if we add that cube root of 9, then it works. But if we just have cube root of 3, it does not. Alright, and this is Gaussian integers, which I imagine they'll do more with later, so we'll kind of be, like, lax on the details for now. So let R be a ring of 2 by 2 matrices of the form AB 0, 0, or AB isn't 0. Show that R, although R is a ring that has no identity, we can find a subring R, S of R with identity. So this is a kind of funky one. So we have A, B, 0, 0, and we just have our subring of this be the set of all A, 0, 0, 0, which clearly has identity. So we can find a subring of a ring with no identity that actually has identity, which is really weird. Alright, list or characterize all the units in the following rings. So the units are going to be elements. Yes, okay. So the units are going to be, if z mod n, we have z mod n. The units are going to be the set of all m, m in z mod n, such that the greatest common divisor of m and n is equal to 1. Because then, this is Sm plus Rn is equal to 1. So Sm is equal to negative Rn plus 1, which implies that Sm is congruent to 1 mod n, which is the same as literally saying that it has a multiplicative inverse. And then conversely, we can just go in the literal opposite direction. So in these cases, z mod 7, everything is a unit. Z mod 12, every number that is does not have 2 or 3 in its prime factorization will be a unit. Z mod 10, any number that does not have 2 or 5 in its prime factorization will be a unit. So M2Z, the 2 by 2 matrices entries in Z. Okay. So we want to find A, B, C, D times E, F, G, H minus 1, 0, 0, 1 is equal to 0, 0, 0, 0. So this is the same as saying AE plus BG, BG, AF plus BH, CE plus DG, CF plus DH. So we have this is equal to 1, 0, 0, 1. So we have A, E plus BG is equal to 1. We have that CF plus DH is equal to 1. We have that CE plus DG is equal to 0. And we have AF plus BH is equal to 0. And obviously these are symmetric, so alright. Can we like use any identities over these? E plus HG is equal. So we have AE plus HG is equal as well to CF plus DH. Oh. Huh. That is weird, right? Because they're both equal to 1. And we have that CE plus DG is equal to AF plus BH. So we have that AE plus HG minus CF minus DH is equal to CE plus DG minus AF minus BH. Which is simply just like subtracting these to the sides and realizing they both evaluate to 0. Oh, this might be very strange. This might be very strange indeed. So then we subtract both sides onto the left, and we get A minus C times E. So we subtract plus alright, we want to write things in terms of A, C, F. So let me write this out more. So then we have minus CE minus DG plus AF plus BH. So we subtract that, and we have this is equal to 0. Right. A plus HG minus CF minus DH. So first let's factor out A plus BH. The entire time I've been writing that, it should be a B. That makes sense, yeah. Okay. So now we have that A minus C E plus B minus D G plus A. Oh! Ooh, what? Excuse me. A minus C F plus B minus D H. B minus D H is equal to 0. Which we can then factorize this out to get A minus C times E plus F plus B minus D times G plus H is equal to 0. Which allows us to, let me bring this over here a little bit. And this gets us that A minus C E plus F is equal to is equal to D minus B G plus H. So let's think from here. I mean, so A minus C wait, let me think about this more carefully about what this means. This means oh gosh, I feel like there's something this should mean, but I'm not getting it yet. Ah, okay. So like, let's work out some examples then, I suppose. Wait, I mean, if I work backwards through this, okay, it's not necessarily true. It's close to being true. Because we also have the conditions that these things evaluate to 1. Oh, shoot. Oh god, I probably should just like refresh my mind on what the inverse matrix is instead of trying to like work all this horrible system of equation stuff out by hand. So like, okay. mean, the thing is, one thing we get from this is that, first of all, one of these two terms has to obviously be non-zero. Yeah, one of these terms obviously has to be non-zero. So we'll be able to divide it out, and to basically, like, if we'll be able to get something like a minus c over d minus b times e plus f is equal to g plus h. And this is interesting because it relates the vertical things up here with the horizontal things here, which that's really weird. Oh shoot, okay. I mean, one thing we can do here is we can kind of cheat and say that there's a invertible matrix that just like permutes the elements. So we can assume, for example, that A is always going to be non-zero. Okay, yeah. Let's do this full thing. Let's do this full thing. So we have this. So we're able to create a kind of like almost disgusting thing. Assume A is not equal to 0. If A is equal to 0, then we literally just apply a permutation matrix to this, solve it when that's the case, and then like permute it back. This means that we get E is equal to 1 over A minus BG over A. We also get that F is equal to negative BH over A. So we have those two we got from case. So CE is equal to C over A minus BGC over A plus DG is equal to 0. Which also gives us that C minus BGE plus DGA is equal to 0. Oh gosh, you know, I'm not even gonna worry about this. I'm not even gonna worry about this right now. This is some horrible linear algebraic stuff. So for the sake of time and also my sanity, it's this one. I'll do this later. I will try to link to something which actually gives the proper description of it, instead of just me being super lazy. Also, it's mainly because I forget the like inverse of a matrix formula. If I remembered that, then it's like really simple, because it's basically confirm. First of all, your matrix has to have either determinant 1, or it has to be a special thing where the determinant divides all the entries of your thing. So it's like not exactly trivial. It's weird. Okay. And all the ideals in each of the following rings, which of these ideals are maximal and which are prime. These two are kind of easy. Yeah, they should be kind of easy because all ideals, you can think of them as principal. I'm pretty sure they're principal ideal domains. M2R, the 2x2 matrices with entries in R. So like, if we suppose that AB, wait, let me think. 2R, 2. So first of all, something interesting to note is that whatever Whatever the ideal in this must be, we must include all possible like determinant 0 matrices in this. I'm just wondering if every ideal is principal in this. So we have an ideal. Let's think. Oh gosh. 2 by 2 matrices to interest in R. Which of the ideals are maximal and which are prime? God, I can't think straight. Like, I think it's... Oh, God. The thing is, there are so many matrices that I can't think of all possible ideals. Oh, wait. I'm thinking. Oh. Okay. That's kind of cool. Alright, so we have basically 2 cases for ideals. So if we have an ideal, suppose there's a matrix A in an ideal I of mn of R. We can actually use mn instead of m2 of R. We might do m2 of R later if we want to be more specific. Such that the determinant of A is not equal to 0. Then there exists an A negative 1 with A negative 1 equal ID. So ID is an I, implies that I is equal to mn of R. So basically, any ideal that contains... Yes, okay. Any ideal that contains a matrix of non-zero determinant is the entire set of matrices. So the only other ideals are the ideals of determinant 0. Suppose, for the example in M2, let me think. So like, let's think of the ways. Suppose we have a matrix A, B, C, D. Then, included in the ideal will be C, D, A, B. Will be B, D, A, C. Will be its like permutations around functionally. I'm wondering if that means... Is there a way... So there's a 0 ideal. Is the only other ideal the ideal of all... Suppose we have A, B, C, D. And note that AD minus BC is equal to 0. And suppose we have a matrix E, F, G, H, such that EH minus FG is equal to 0. Is there a matrix that takes ABCD to EFGH if A is not the 0 element? Not necessarily. Oh. Oh, that is bizarre. Oh, that is really weird. Oh my god. Okay. If this might be what I think it is, and if it is the case, that is weird. So, if we have our zero ideal, right? We have next this ideal. What this ideal is any non-zero any matrix will either take zero this to the one matrix, or will permute this one entry. If we have two entries, it will either permute this or bring it back here. I'm wondering. Not necessarily. Two matrices are where things get really complicated. So there is definitely an ideal. Wait, okay. Wait. Oh, this is weird. Alright. So this is obviously its own thing, but if it permutes. Oh. So like, okay. It's funky. So clearly, we can pick out A0. Clearly, any matrix where we have even just a single, we can take any matrix and we can create it. We can alter it so that it is just the matrix of the form A000 for a single entry. Now, we can permute it to be 000A. We can divide them to get the matrices 1 0 0 0 and 0 0 0 1. But then adding them gives us our identity matrix. So the only ideals in this are, oh my god, the only ideals in the general linear group. And this will also like work regardless of what you do, just doing certain permutation matrices stuff. In the general linear group over the real numbers, note that it's over the real numbers here, because we have to take this zero divisor. We need to be able to divide the general linear group over a field K, to use later linear algebraic terminology, has only the ideals of the zero ideal and the entire ideal. It's more complicated when you have integers, because you can't necessarily divide out by this stuff. Oh my god, that is cool. That is so cool. Oh my god, okay. And that explains why later on, find all ideals in each of the following rings. That explains why the integers come after the real numbers in terms of difficulty, because in the integers you can't ensure division, while in the real numbers you can, so you can take that extra step. I'm gonna leave the integers as exercise, because I'm lazy. And Q. And Q, similarly, what it will be is that since it's, okay, kind of like little thing is that if we have a field, then the only ideals are the max, the only ideal is the trivial ideal or the entire space. It's not condition, it is not sufficient to say that a field is something where that holds, because we saw an example, M2R is not actually a field, but it still holds. That we only have the zero ideal and the principal, the zero ideal and the any ideal. Yeah. Man. Alright, for each of the following rails. Nah, I'm good. Find all homomorphisms. I can probably do this. Just quick reframing of a previous argument. So all homomorphisms, z over 6z to z over 15z. So we know phi of 1 must be some number such that 6 times 1 is equal to 0 mod 15. And, okay, it's actually not completely trivial in this case. So we can send phi of 1 to, alright, so this has the factorization 3 times 5. This has the factorization 3 times 2. Oh, actually, we only have 2 cases. So we can only define it to be 0 or 5. Any other case will fail. Or actually, 0, 5 times n for n equals 1, 2. So 0, 5, 10. So we know that there are only 3 possible homomorphisms, because this also is a homomorphism between abelian groups, and they're determined by where phi of 1 is sent to either 0, 5, or 10. To determine all ring homomorphisms, are all these homomorphisms ring homomorphisms? That's the important question here. Final homomorphism, Z over 60 to Z over 15, Z. I mean, phi of AB is equal to phi of A, phi of B is equal to A times phi of 1, B times phi of 1. So we know that has to hold. So yeah, I'm pretty sure from the looks of it, the homomorphism should hold. Or actually, I'm thinking. So phi of 3 times phi of 2 would be like, okay, actually phi of 3 is sent to us, that's fine. We need to find another example. Phi of 3, phi of 5. 3 times 5 is equal to 15. He's not divisible by 6. So we know that phi of 3 times phi of 5 will be equal to 3 times 5 times something, which will be equal to 0, is mapped to 0. And I'm pretty sure, like, from the looks of it, it looks like this rule holds in all these cases for the cyclic groups. Yeah, I'm pretty sure it will just hold. So yeah, we will be able to uniquely characterize it by 0, 5, or 10 here. Okay. Prove that R is not isomorphic to C. They're not even isomorphic as abelian groups, so they obviously can't be isomorphic ring-wise. Or no, actually, you can't really say that. It's more so that the multiplicative group of R is not equal to the multiplicative group of C, because there's no element in R such that multiplying it 4 times, multiplying it 3 times gets you back to, 4 times gets you back to itself, minus -1. Or no, yeah, there's no element squared that equals -1. That's like literally the definition of C. Yeah, what am I thinking? Okay. Proof or disproof? This is not true. So suppose it was. This means that phi of a plus b root 2. Phi of a plus b root 2. So like a plus b root 2 squared, b root 2 squared is equal to a squared plus 2b squared plus ab plus 2 ab squared 2. And it's easy to see that there's this doesn't hold in root 3 because of this 2 here. So like there's an element square root of 2, there's an element 1 times square root of 2, such that when you square it, you can say square it and divide by 2. Square and divide it by that element squared. Oh no, square, yeah, is equal to 1. Not 1, is equal to 2. So like there's some number square root of 2 a such that square root of 2 plus 1 square root of 2 minus 1 is equal to 2. And then if you try to like apply an isomorphism to that, what you'll fundamentally get is that it just will not work in that case. Alright, how do I best express this? Yeah, that's the best way I can do it. So let's think about this. So let's suppose we have some isomorphism, phi plus a plus b square root of 2 goes to like a prime plus b prime square root of 3, where a prime and b prime should be functions of a and b in this case. Well, first of all, let's note that phi of a is sent to a prime. Is sent to a prime plus 0 times square root of 3. Why? So, let me think about why specifically. So, phi of a so if phi of a squared let me think carefully about here. Okay. So a prime plus b prime square root of 3 squared equals a prime squared plus 3 b prime squared a prime b prime. Phi of a times a, phi of a squared, would be equal to that expression there. It's 3a squared a prime squared plus 3b prime squared plus 2a prime b prime squared of a. I'll probably have to use something distributive here. Let me think. Because I feel they're not isomorphic, right? Because square root of 2 satisfies... My brain is blanking hardcore. Okay. Oh, okay. I think I get it. So we have that phi of 1 is will be equal to 1 no matter what, right? So phi of a plus b squared of 2, because of this addition right here, is going to be 1 plus phi of b squared of 2. Right, so it goes, if phi of L1 is 1, and phi of A not equal to A. Okay, so let's think about it. First of all, let me try to prove some more elementary properties before I worry about all this. So an isomorphism from the rationals. So it takes phi of 1 to 1, obviously. It takes phi of 0 to 0. Phi of 0 equals 0. And from this especially, it follows that phi of n equals n for n in Z. Suppose we have phi of P over Q is equal. So phi of P over Q times Q equals phi of P over Q is equal to phi of P over phi of Q. Because of the multiplicative properties of this. And we're just writing it in this way. So it is equal to P over phi of Q. And because phi of Q, oh yeah, oh wait, they're both integers, so yeah. So, okay, phi of P over Q times phi of Q equals phi of P, which implies that phi of P over Q equals P, implies that phi of P over Q is equal to P over Q. So this is a way of showing that an isomorphism fixes the rationals. So this is a way of showing that phi of a plus 0 square root of 2 is equal to just a in that field. Alright, so we simply need to determine how phi acts on this. So suppose we have phi of a square root of 2. It will be equal to a prime plus b prime square root of 3. Right? Now, phi of a square root of 2 squared. One direction is that this is equal to phi of 2a squared is equal to, because you can factor out that group multiplication, is equal to 2 phi of a squared is equal to 2a prime is in this direction it is equal to phi of a square root of 2 squared is equal to a prime plus b prime square root of 3 squared is equal to a prime squared plus 3 b prime squared plus Alright, I'm not exactly out of the woods yet in this. So a prime squared plus 3b prime squared plus, and then we have a b prime square root of 3 multiplied by itself added twice, so 2 a prime b prime square root of 3. And now let's compute this. This is equal to 2a squared. Oh yeah, literally, because a is a rational number in this case. So in this case, we have that either. So in this case, we want these two to be equal. So we have 2a squared. Well, obviously, either a prime or b prime has to be 0. If a prime is equal to 0, then we have 3b prime squared. So we get 2a squared is equal to 3b prime squared. But then we take square roots of both sides, and we get that square root of 2a is equal to square root of 3b. Which is only true if a is equal to b. Yeah, it's only true if because then we get a over b is equal to square root of 3 over 2. And it's simple to show that this has no rational solution in terms of a and b. So then in that case, we have that if... Oh, because then if b prime isn't equal to 0, we never hit any of the elements b prime squared to 3. Which means that the map isn't an isomorphism, which shows that, Q adjoined root 2 is not isomorphic with Q adjoined root 3. Okay. What are the characteristics formed by the set of matrices entries in Z mod 2? I mean, I think it would just be 2, because you multiply anything by it, you add anything to itself, and it's always 2. I forget if it's times, though. Let me double check. Characteristics. Maximum prime ideals, the isomorphism theorems. Decided. Principle. Alright, the characteristic of the integral domain. Okay. To be the least positive. Alright, so yeah, if we add it to each other, then under the addition of Z mod 2, we have that Z mod 2 is going to have a characteristic 2. Define a map phi from C to M2 of R. By that, show that phi is an isomorphism C with image in M2R. It should be obvious that it's injective. It's mainly just showing that it's surjective. Oh, with its image. Yeah, obviously this is injective. And previously we showed that the multiplication structure on C star, or the set of units, has that. The set of units works nicely. So, yeah. In short, this holds. I'm not going to worry about scrambling all the details together. Show that Gaussian integers z adjoint I are an integral domain. So, suppose that a plus bi, c plus di are equal to 0. Then ac plus adi plus bci minus bd is equal to 0. So we have that AC minus BD plus AD plus BC I is equal to 0. That is correct. Yes, it looks correct. So for this, first of all, if this equals 0, then AC minus BD is equal to 0. So C is equal to BD. So AC is equal to BD. So let's think about the possible cases we have. So we can assume that either A or C is not equal to 0. Because if both A and C are equal to 0, actually wait. Alright, so if both A and C are equal to 0, C minus BD is equal to 0, AD plus BC. Yeah, if A and C are equal to 0, then either B or D are equal to 0. But that would just mean that one of these terms is 0, which means it's an integral domain. So we can suppose that, in this case, just by symmetry, A is not equal to 0. So A is not equal to 0, which gets us that C is equal to BD over A. And plugging that in here gets us AD plus B squared D over A equals 0. Which gets us that by the distributive property, A plus B squared over A D is equal to 0. So we have two cases here. If D is equal to 0, then BD is equal to 0, which means that C must be equal to 0 because A is not equal to 0, so C and D are equal to 0. So we can assume that D is not equal to 0. So A plus B squared over A is equal to 0. Because we know A is not equal to 0, we can multiply to simply get A squared plus B squared is equal to 0. Which means that both A and B must be equal to 0, because these are both positive, that's the only way this would hold. Which implies that A and B are equal to 0. Wow, okay, when I got that formula, I thought that was going to be a monster. That was actually a really nice problem. So yeah, the integers mod I are an integral domain. In fact, the rationals adjoined with I are also an integral domain. In fact, the real numbers adjoined with I are an integral domain because the complex numbers are a field. And a field is an integral domain, and any subring of an integral domain is an integral domain. That's a faster way you can prove this, but that's also a more direct way you would do it. Also, give me a second. Yeah. Oh, give me 1 second. Another short intermission. This won't be a long intermission. This will just be something because there's an update and some personal stuff going on for marching band. Yeah, apologies for the delay in that. We had some stuff with weather where a weather update was canceling an event planned for later today. Which sucks, because in that case, it's this event called the Spaghetti Dinner, which actually isn't a spaghetti dinner, it's just a place for a bunch of musicians to, like, hang out and do cool stuff. But it means more time for math, so I guess you'll lose some, you get some. Alright, so now continuing. So Gaussian integers are an integral domain. Excuse me. Yeah, a lot of this is a plus b squared of 3i is a subring of a subring of the complex numbers, and the complex numbers are an integral domain, so this will be an integral domain as well. I'm not gonna spend any more time elaborating on that. Oh gosh, my internet. Alright. No. Parallel computation, not really interested in that. If R is a field, show the only two ideals. Yeah, this is kind of what we previously show. If R is a field, suppose A is in R, like an ideal. Then A to the negative 1 exists if 0 is not equal to A. Then A negative 1 is in A negative 1 times A equals 1 is in I, implies that I is equal to R. Alright, yeah, this is basically to prevent, if S is onto. Yeah, there we go. If R is a commutative ring, then phi of R is a commutative ring. This should be easy, because phi of AB is equal to phi of A, phi of B is equal to phi of AB is equal to phi of BA is equal to phi of B, phi of A. Alright, so R phi of 0 is equal to 0. This is just a normal group, the fact that it's a group homomorphism thing. Let those be the identities. If phi is onto, then phi of A is not equal to 0 for some A. So in that case, phi of 1s A is equal to phi of 1s of A of phi of A equals phi of A. So that implies that phi of 1r is equal to, don't mind the change in notation there. Okay. Forget the associative law and distributive law. Okay, if R is a field and phi of R is not equal to 0, because that's always the case, then phi of R is a field. That'll just be a normal multiplicative inverse thing. Alright, prove that the associative laws for multiplication and the distributive laws hold in R over I. Nah. The second and third isomorphisms. Hey! With those, it'd probably be a good review, but I'm going to be honest, I'm kind of too lazy to do it. There's so many other cool things. There's so many other cool exercises. Shh. I don't want to be reproving old things. Okay. Alright, so let R be a ring and S be a subset of R. Show that S is a subring of R if and only if the following conditions are satisfied. So, this is obvious. It must not be vacuous. This is like just the closure operations. So, suppose S is not equal to 0, not equal to the empty set. Rs is an S and R minus S is an S. So basically, we have R. First of all, we have that since this is not equal to 0, there exists an R. So R minus R equals 0 is an S. And as well, this gets us that 0 minus R is an S. So if R is an S, R minus R is an S. And similarly, R minus S equals R plus S is an R. So, and this is also the abelian group, so plus is a subgroup, And then this just ensures that it's closed under multiplication. And then the other multiplication rules are inherited from the base place, so yeah, that's really it. Let R be a collection of subrings. This is the same thing. I can example this show the union of two subrings. Like, you can use literally the example with abelian groups to show that it's false. The extra thing you just have to prove is that the multiplication is there, which is just kind of like trivially true. Let I be an addition of ideals in a ring R. Yeah, okay. This is actually, I'm gonna prove this because it's nice. Okay, so we'll prove it basically by induction. You can just take this infinitely far out. Actually, okay. So A with like A with just like an indexing alpha, we have that is equal to, okay, let's call it, and we have this, and we have K is equal to the intersection of IA. I want to show it's an ideal. So, first of all, the subgroup shall, since each of these are subgroups, the intersections of subgroups is a subgroup, so it's still a subgroup. To show that's an ideal, suppose we have A times R for R in I for R in K. Then R is in the intersection of all IA, which means that AR is in IA for all A, which implies that AR is in the intersection of IA. And that shows that the note here as well, we have the arbitrary intersections. We don't necessarily get this for unions. We do have some like relations of like finiteness when we have prime, like certain types of prime ideals. But in terms of just like regular ideals, we can only ensure intersection. And this does, in case you're wondering, in case you know, this does have relations to topology. And this has the idea with something called like the spectrum of a ring. Alright, anyways, I was getting like really overly excited about that. Alright, integral domain. Show that if the only ideals are R and 0. Oh, okay. Let R be an integral domain. Show that if the only ideals in R are 0 and R itself, R must be a field. Okay. So suppose that we have R is int dom. Alright. And suppose that we have an element A in R and take its principal ideal. Right, we have A and R, we take its primary ideal if A negative 1 does not exist. If A negative 1 does not exist, A 0 is not equal to that, is not equal to R. Actually, we do have to be slightly more careful about that. R is an integral domain, right? A is an R. Actually, I think this needs a bit more proving. So, if R must be a field. We should be able to use the fact that A negative 1 does not exist to show something. So R is an integral domain, A is an R. The principal ideal generated by R. So if A to the negative 1 does not exist, then alright. So, okay, we have the case R by supposition. Which means that B times A is equal, B times A is equal to 1. Every ideal always contains a principal ideal. I think I'm getting it now. Which means B times A is equal to 1. I'm just wondering where the assumption that it's an integral domain comes in. So A is an element of R. By supposition, the principal ideal of A is equal to the entirety of R. Because it's an integral domain, we have that it's a ring with unity. Is a commutative ring with... No, not necessarily a commutative ring with unity. Shoot, oh my gosh. So, like, let's think a bit more. Zero. Like, this seems just way too simple. I can't make heads or tails of it. Do we define it to be an integral domain so that we have unity? Alright, this is page 219. Let me scroll way back up. Because it could just be they're defining an integral domain. Okay. I feel like this works for any commutative ring with identity that you have that hold. Because the logic is really just simple. Because if there's an ideal other than those, then it contains a principal ideal. You just take any element, you take its principal ideal. Clearly that principal ideal will be like a subset of that. So you have that principal ideal. And so showing that every principal ideal is equal to the entire thing, since every ideal contains a principal ideal, means that every ideal that's non-trivial goes to that. So it doesn't look like an integral domain is necessarily required from the looks of it. Okay. Let R be a commutative ring. An element A is nilpotent if A to the n is equal to 0 for some positive. Alright. Show that the set of all nilpotent elements forms an ideal. Oh, this is actually really easy. So, suppose that A to the n is equal to 0. And suppose that we have multiply b times a. We have b times a to the n equals, because by commutativity, b to the n times a to the n equals 0. So it's nilpotent of n. So nilpotent elements form an ideal. A ring R is a Boolean ring if for every a in R, a squared is equal to a. Show that every Boolean ring is a commutative ring. Alright, so we have that AB squared equals AB. So we have AB is equal to AB. We multiply on the left by B. So we have B, A, B, A, B, A, B is equal to B, A, B. So this is equal to, because of idempotence, B, A, B is equal to... Alright, wait, I'm doing this wrong. I'm being dumb. Give me a second. So AB, A is equal to A, B, A. Show that if every Boolean ring is a commutative ring. So then we have so we have, oh, because we don't necessarily have cancellation here. Alright, so let's think carefully. So if AB is equal to BA, then we're able to multiply on the left by AB equals ABA, which is equal to AB, which implies that AB is equal to ABA. False. It's equal to ABA. Then we multiply on the right side by B to get AB is equal to ABB is equal to AB, which gets us that AB is equal to ABAB, which is the statement that AB is equal to AB squared. So then we just do these like implications in reverse. We expand, we factor this out, we bring this out, we bring the B out, we expand that out, then we're able to are we necessarily able to cancel it? Wait, so AB is equal to AB squared, which gives us AB is equal to ABAB, which gives us that ABB is equal to ABAB. I just don't know if we necessarily have a cancellation law. ABB. Oh gosh, I'm being dumb. Because we can go one way, right? I just don't know if we can go the other. Let's think about this. So we have AB is equal to AB. We multiply on the left by B to get BAB is equal to BAB. Then we multiply BA is equal to BA. Same thing, okay. I'm wondering, what if we take AB minus AB, we get 0. So let's work in the fact that we have a ring structure as well, not just a like almost group structure. So we can factor out an AB to get AB minus 1. AB minus 1 is equal to 0. Let's think. So we have this here now. What can we do with this? I mean, we could sneak in this. AB minus 1 is equal to 0. And we could left multiply to get AB B minus B is equal to 0. Also, all my B's look like H's. Oh, it's frustrating. Alright. So we have this. Ah, God, the question again. What can we do with this? Oh, my brain is really not on it today. So AB, BAB, minus B is equal to 0. Alright, let's revert this. Let's completely rework our assumptions. So suppose that AB is equal to BA. This is the same as saying that AB minus BA is equal to 0. AB minus B is equal to 0. What can we do with this? Well, if it's 0, no. You can multiply on the left side by A to get AB minus ABA is equal to 0. Then we factor out the A to get B minus BA is equal to 0. Then we get AB 1 minus BA is equal to 0. This is AB. Yeah, minus. Oh my gosh. A ring R is a Boolean ring for every A apply. We can't necessarily reverse that though, that's the main issue. I'll work on this a bit more once more, starting from first principles, seeing where I can get. So we have that AB squared equals AB. Or AB squared equals AB. So AB equals AB. AB equals AB, which means we have AB minus 1 is equal to 0. Or actually, more generally, we have that using that line of logic of replacing AB by A. We have that, I'll put as a star here. A times A minus 1 is equal to 0. Now what can can I do from here? Well, I can do an interior multiplication by b to get AB, BAB minus b equal to 0. We can factor out then AB, BA minus 1, B is equal to 0. Which gets us that A, B, A minus AB multiplied on the right side by B is equal to 0. ABA minus AB. I mean, we can pull an A out of there on the right hand side to then get that A, BA minus AB times B is equal to 0. From here, if we have an integral domain, then our stuff is really easy from here. B minus BA minus 1, B pull out the right. Then we distribute inside by the A, then we pull out the A from the left. So we need to now show okay, what we need to now show also, I should probably just have this highlighted. Yeah, 29. So all we're assuming is that R is a ring. Not even that the ring is commutative. Or at least initially. So first of all, if we expand, we get A, B, A, AB, AB minus AB is equal to 0, which makes sense. This obviously holds true. So I just wanted to sanity check myself there. Alright. The main difficulty from here is that what if, okay. BAB. So we also have that A, B, AB minus AB, B equals 0. Oh, I just can't get rid of these stupid A's on the side. Well, in this case, I mean, I guess what we can do is we have A, B, A, B, A minus AB. And we pull out the, oh wait, actually, let's think about this. So we have from here, A, B, B minus 1, A, B is equal to 0, which implies that A, B minus 1, A, B is going to be equal to 0. Does this get us anywhere? Does not look like it. Shoot. Yeah, okay. What problem is this? 29? I'll put this off for later, but for the sake of time, we will continue for now. Because a lot of it is, the difficulty here is showing that the commutativity holds. Oh, wait. Before I continue, I was very dumb. Please let me write a, okay. I feel dumb. I feel very, very dumb. Alright. I think I did discover something here. I just didn't know that I did at the time. We also have A1 minus B, because our group has an abelian structure. So A minus BAB equals 0. So we have that A minus BAB is equal to 0. So we have that A. Wait, is that right? No, it's not. Okay, that explains it. Alright, so A, B. So we have A, and then we multiply by AB, minus BA, B is equal to 0. A, no, okay. Shoot. Unless there's something that can like switch the structure, the abelianness of the addition can switch the structure somewhere in here. So maybe it must be. Yeah, okay. I just need to shelve this for now. I don't like doing that, but I'm gonna have to do it for now, just for sake of time. Alright, and that's a similar problem. Let R be a ring with identity and with identity 1R, and S a subring with of R with identity 1S. Not necessarily for 30. We saw the example with a set of 2x2 matrices, and the 2x2 matrices of the form 1, 0, 0, 0. That has a different identity. Yeah, it has a different identity, just straight up. That is weird though. We do not require the identity either to be distinct from 0. Yeah, this just comes from the fact that, like, if 1 equals 0, then A times 1 equals A, is equal to a times 0 is equal to 0. So every element is equal to 0. It's very boring. To find the center. Summing prime ZP. Gosh. Produces every finite integral domain is isomorphic to C mod P. Just seems instinctively a bit off time. Like, it sounds like you can just have like a Boolean structure. The automorphisms, the inner automorphism stuff again. Cartesian product of a ring, pointwise, idempotent, fx versus x. Prove that the only idempotents in an integral domain are 0 and 1, obviously. N equals D, and GCD of PD is not equal to 1. Solution. Remainder theorem for rings. Oh, the mod I mod J notation, I love it. I can't, J. Yeah, I'm getting tired. Oh man, I spent way too long on this dumb problem. It's been beating me down. Okay. I guess since the rest of these aren't particularly interesting, I'll just work at problem 28 on stream a bit more and see if I can find anything. So AB squared is equal to AB. So we have that AB is equal to AB, which means that AB minus 1 is equal to 0. Now I'm wondering, alright, if xy is equal to 0, is yx equal to 0? Because I feel like this is the fundamental commutative boost I need. Xy minus yx multiply on the left hand side by x to get x y minus x yx to get xy minus xy 1 minus x, which is equal to 0. Now the main issue is that it doesn't, it shows that xyx is equal to 0. Yeah, I feel like this is fundamentally like the thing we need. So xy minus yx yx xy minus yx yx. Hmm. Oh gosh, I can't think about it straight. Okay. So also, I'll go back to highlighting this. Oh wait, no, wrong one. This one. Okay. A squared. Yeah. Sorry, so let's proceed with the case that if xy is equal to 0, then we'll just have this as a lemma. Then yx is equal to 0. So first of all, we can then take a b, multiply it, b is equal to b squared, and distribute it to get ab. AB times BAB minus B. BAB minus B is equal to 0. We take this, and then we have BAB minus B times AB is equal to 0. Actually, I wonder. Wait, let me think. BAB minus BAB. So this is equal to 0. So this is like, if we assume this is 0, then it's commutative. So let's focus on this. AB times AB minus 1 equals 0. So we can have that. BA yeah, we swap stuff around and we can get BA AB minus 1 is equal to 0. Then BA wait, let's think. So we can basically, now if we have this true, we have arbitrarily many A's and B's. So we can take it AB minus 1 is equal to 0. And we can get stuff. So I'm thinking what we then do is we have this. We plop that B down into it to get AB, BAB minus B. Then we take an A to get BAB minus B. Okay, something I'm seeing now. Because of how we're having things on the right side, the thing on the left side is always going to be the same. So we need to find some way to permute this. Oh my gosh, okay. So we have a minus 1 is equal to 0. So let's think. So let's just see what we can formulate here. So we have x, y, minus 1 is equal to 0. Let's think. So this is equal to xy. This probably is where we need to go. Xy plus y minus x xy plus y minus x minus 1. So we have that's equal to xy minus 1 xy minus 1 plus y minus x. This would be a really unorthodox approach to go for, but I'm thinking every element can be written as x plus 1 or x minus. Every element can be written in the form of this. Also, I'm double checking. Do we even have. Wait. We don't even have unity. We do not even have unity. Okay. AB squared equals AB. So AB, or is it with AB? Now I want to factor it out, but I can't because of the 1. So AB minus AB plus BA is equal to BA. So let's think. If we have A plus B A minus B. Oh, this might be it. A squared plus A plus B, A minus B is equal to A squared. It shouldn't be plus, it should be minus. A squared minus B squared. By just distributivity. Oh, actually, we have A, B. Okay, we don't yet have that. So I need to be very careful with what I say here. So A squared plus, yep, let me write this in order. A squared minus AB plus BA minus B squared is also equal to A minus AB plus BA minus B. Oh, it's a useful reduction. I'm just wondering what we do with that. I mean, this means that from here at least, we have that BA minus AB is equal to A plus B, A minus B plus B minus A. Let's think about this actually. Let's think about this a bit more. Wait. Okay. Brain think. So this B minus A. This is -1 A minus B. We don't necessarily have I mean, we have a kind of substitute. So we have minus A minus B. Minus A minus B. And this is actually equal to A plus B. We can multiply this by itself because this is equal to A minus B squared. This is equal to A plus B minus A minus B all times A minus B. Oh, okay, that's nice. That's very nice. So from here, we can do subtraction. So we have A, this subtract A. Let me double check that I have this all correct, because this is potentially kind of huge. Okay, so a plus b times a minus b is equal to a squared minus ab plus ba minus b squared is equal to a minus ab plus ba minus b. Yes, that difference comes in there naturally. I'm wondering, actually no, this might be more useful as a form. We'll see in a second. So we have, we rearrange that, we get this formula here. And this formula, the a's cancel. And we get 2 times b times a minus b is equal to b a minus ab. Actually, let me write it as this. So b plus b. Okay. Pull back my screen a little bit. Alright, so what is this? So we distribute this on the left, so we get BA minus BB BA minus BB plus BA plus BA minus BA plus BA. Okay, let me double check this because that's very strange. That doesn't seem right. Okay. So you have A. So let's recheck all this. So we have A plus B plus times A minus B. So we have A squared, A times A minus B, plus B times A plus B times B. We use a reduction, and that gets us this formula that BA minus AB, which is just this rearranged, equals A plus B, A minus B, wait, let me check something real quick. Let's double check at the point of this formula. So we have A plus B, A minus B, and then we add B and subtract A. Which is the same as subtracting minus A minus B. Now we use this rule again to get that A plus B, A minus B, minus A minus B, A minus B, which lets us pull out A plus B minus A minus B A minus B. So we evaluate within here to get this is equal to B plus B, correct? B plus B times A minus B. B plus B, A minus B. Which this is BA, BA minus AB is equal to BA minus B plus BA minus B. So we have that negative AB is equal to BA minus B minus B. I mean, this looks true, but that's bizarre. Okay. But I think this rule goes, this is a useful identity. So, wow, okay. BA, or no. AB is equal to, yeah, because we're flipping around everything with a negative, is equal to B plus B minus BA. So after all this wild stuff, we have this absolutely insane identity. Like, the more I try to prove this, the more it looks wrong. So we have that. And so taking this thing over here and moving it over like here, we have that AB, AB. We can probably do AB, B plus B minus BA minus AB is equal to 0, which gets us that AB plus AB plus AB minus ABA minus AB is equal to 0. We cancel these two and get that AB minus ABA is equal to 0. So we then distribute to get A, B minus BA is equal to 0. And now the thing is, oh, okay, so we're nearly there actually. So I actually was kind of right in one of my earlier assertions. Oh, this is such a bizarre problem. So if this is true, and we suppose we can commute these, this would give us, oh wait, no, it actually wouldn't give us anything. Shoot. Okay, let's think. Well, no, okay. From here, this identity also gives us that plus, that, minus BA equals AB minus B minus B. So A, B minus, or no, plus AB minus B minus B is equal to 0. We cancel one of these out. No, oh my gosh, I just can't get it. Oh man, I think I'm just gonna have to like give up because I'm like running into this mental roadblock. Oh gosh. Yeah, I think if I decide to stream again at some point later today, because like I have a whole day free, so I might, then like it's very possible for me to work out some details to this. And I'm pretty sure there is stuff later in the book, if I remember correctly, that it goes over. A ring, okay, oh man. I don't want to leave it at that. But I feel like I might have to. Just because, like, I've already been streaming for, like, God, 3 hours or something? Yeah, 3 hours, 24 minutes. So... like there's not really that much else to do, and especially polynomials are going to lead to a lot of cool stuff because polynomials over general rings are very powerful. So okay, I'll partially compromise. At the beginning of next stream, I'm going to, whether or not I actually solve the problem independently, I'm going to give the solution to the problem before I actually do the reading, because I can't just like do this much work in a problem and just like leave it like that. Problem 28, that's ridiculous. But for now, I will be stopping the stream just kind of for my own sake, and because I'm tired and want to rest up a bit before I do anything else math related. So thanks.